Spherical capacitor. In this lecture, we will assume a spherical capacitor with some charge on its inner surface and an equal amount of charge with opposite polarity on its outer surface. Then we will create an equation for capacitance by determining the voltage difference between them for a given charge on each. Formula used. Number 1. The electric field outside a charged conducting sphere is given by E is equals to Q over 4 pi epsilon naught times R squared. Number 2. The potential difference between 2 points A and B is VA minus VB, which is equals to negative times the integral E dotted with dr vector with limits going from RB to RA. Number 3. Definition of capacitance. C is equals to Q over delta V. Geometry. Consider a spherical capacitor with a positive plus Q charge on the interior surface and a negative minus Q charge on the exterior surface. Let A and B be the inner and outer surface radii respectively. The radial distance between the two charged surfaces is B minus A. Let V1 represent the potential at the inner spherical surface and V2 represent the potential at the outer spherical surface. Let C denote the required capacitance of the spherical capacitor considered. Derivation. The electric field outside a charged conducting sphere is found by applying Gauss's law to it. E is equals to Q over 4 pi epsilon naught times R squared. Recall that VA minus VB is equals to negative integral E dot dr with limits going from RB to RA gives the potential difference between 2 points A and B. In our case, V1 and V2 represent the inner and outer cylinder potentials respectively. Thus, V1 minus V2 is equals to change in potential, which is given by negative times the integral E dotted with dr vector with limits going from B to A. Now E vector and dr vector are both pointing in the same direction, so we can write negative integral B to A E dr. Integrating the electric field along a radial line yields the voltage between the spheres. The change in potential will be equals to negative times the integral Q over 4 pi epsilon naught times R squared times dr with the limits going from B to A. Then we have negative Q over 4 pi epsilon naught, thus being a constant, we have pulled it out of the integral. This is multiplied to the integral dr over R squared with the limits going from B to A. That gives us negative Q over 4 pi epsilon naught, solving for the integral, which is a very simple integration, which gives us Q over 4 pi epsilon naught times 1 over A minus 1 over B. Following the definition of capacitance, C equals Q over delta V. So we have Q divided by, so we replace the value of delta V with the obtained expression. We have Q over 4 pi epsilon naught times 1 over A minus 1 over B. Then we factor out Q, which is present in both the numerator and the denominator, and that leaves us with 4 pi epsilon naught times AB over B minus A, which is the capacitance of a spherical capacitor. Isolated sphere. Capacitance exists in an isolated charge conducting sphere. Although applications for such a capacitor may not be obvious, it does demonstrate that a charged sphere has stored some energy as a result of being charged. Using the capacitance expression for concentric spheres, C is equals to 4 pi epsilon naught times AB over B minus A. If B is large enough, that is, when B approaches infinity, we get C is equals to limit B tending to infinity 4 pi epsilon naught times AB over B minus A, which is equals to 4 pi epsilon naught times limit B going to infinity. So we have divided both the numerator and the denominator by B, and that gives us the expression A divided by 1 minus A over B. Now we use the limiting value, and that finally gives us 4 pi epsilon naught A. So this is the expression for the capacitance of an isolated sphere.